Today we'll be talking about section 7.4 and we'll be looking at three key objectives for the day. In this section we'll talk about simplifying radicals. We'll also talk about adding and subtracting radicals. We'll talk about finding the length of the sides of two types of special triangles, 45, 45, 90 triangles and 30, 60, 90 triangles. And at the conclusion of this video, you should have some time to get started with homework number 24. So to start with, you'll need to take out the following materials: your notes from last night's homework, specifically the notes that you started from section 7.4, that is the self-checks. We're going to add some more notes to that today, and so you'll have the opportunity to write those notes down, and then also have some example problems for you to complete right there in your notes. So you may want an additional sheet of paper in addition to what you started with those self-checks last night. You'll also need a pencil and a calculator. So at this time, you should pause the video and take out the necessary materials, and then resume the video once you've got the materials in front of you. Let's start talking about that first objective, which was simplifying radicals. I know that you're familiar with simplifying radicals, so we're going to talk about a couple of key things just as reminders. First of all, radicals in fraction form can be written in one of two ways. If you have a radical that has a fraction for its radicand, you can split that one radical into two separate radicals: a root of the numerator divided by a root of the denominator. So for example, the square root of 32 over 8 would be the same thing as the square root of 4 over 1 once we reduce 32 over 8. And I can make that one radical with a fractional radicand into two separate radicals, where I would make it the square root of 4 in the numerator and the square root of 1 in the denominator, and simplify each of those individually. Similarly, the square root of 16 over 9, which is a fractional radicand that cannot be simplified, can be split into two separate radicals, the square root of 16 over the square root of 9, and then simplify each of those individually. Another key reminder about simplifying radicals, specifically those that are not equivalent to whole numbers, like the square root of 16 or the square root of 9, were radicals that were equal to whole numbers. But if you have a different radical, you can simplify or rewrite that radical in its simplest form by writing your radical as the product of one perfect square or cube, if you're dealing with cube roots, and some other radical, so that when you multiply the radicands together, you get the same product as your original radicand. So for example, the cube root of 16 is not a perfect cube. However, we can rewrite that as the cube root of 8 times the cube root of 2. And the reason I chose 8 times 2 as opposed to other multiples that multiply together to give you 16 is the cube root of 8 is the largest perfect cube that divides into 16. And so I can simplify the cube root of 8 to be 2. And so my final answer in simplest form would be 2 times the cube root of 2. At this time, you should pause the video, and in your notes, try these 5 examples from your textbook. They are questions 28, 36, 40, 44, and 54. Pause, complete each of the 5 examples, and then return to the video at that point in time to check your solutions. So here are the solutions for those 5 questions. Again, it may be helpful for you to pause and go through each individually. I'll walk you through a brief explanation of each of the 5 questions. For number 28, we can take these two radicals and make them into one, and simplify the radicand so that it's a little easier to simplify and come up with 8. Same thing with number 36, except we're dealing with cube roots. For number 40, 250 is not a perfect square, but we can split that into the product of 25 times 10, since the square root of 25 is a perfect square that's equivalent to 5, um, and we would come up with our final answer in simplest form. 44, very similar, just with cube roots. The cube root of negative 8 or positive 8 would be the largest perfect cube that divides into negative 72 evenly. And then for number 54, we have to split that into perfect fifth roots. So in the numerator, first of all, notice we split the one radical into two separate radicals. And in the numerator, the fifth root of r to the fifth is a perfect fifth root. The fifth root of 4 is not simplifiable. In the denominator, the fifth root of 243 is a perfect fifth root, and the fifth root of s to the 10th is also a perfect fifth root. So if we simplify the three perfect fifth roots, we'll end up with r in the numerator, 3 in the denominator, and s squared in the denominator. And if we multiply all of our simplified parts together, we come up with our solution. R times the fifth root of 4, all divided by 3s squared. For the next part, we're going to do a little geometry review. And again, it would be a good idea for you to add these things to your notes. So what I would like for you to do is to take a second, pause the video, and answer these two questions in which I want you to write an inequality that describes which side is bigger. Is A bigger than B? Is B bigger than A? Are the sides equal? How are they related? And how do you know? So for number 1, B is larger than A, and we know that because the side opposite the largest angle, or the larger angle, will be the larger side. So in this case, or in the case of all right triangles, the side opposite the 90-degree angle, or the hypotenuse of the triangle, is the longest of all three sides. However, in comparing just sides A and B, since B is opposite the 60-degree angle, it will be larger than A, which is opposite the 30-degree angle. If we apply that same logic to number 2, A and B should be equal in length since the angles opposite A and B are congruent. A is opposite a 45-degree angle. B is also opposite a 45-degree angle. So they would be equivalent in length, and that's why we refer to this triangle in number 2 as an isosceles right triangle. So if we start applying some of that logic then to a couple of key relationships that we know about special triangles, the first of those special triangles is what's called a 45-45-90 triangle, or an isosceles right triangle. The key relationship you want to keep in mind here is that the hypotenuse, or the longest side of this triangle, is equivalent to the length of either of the legs times the square root of 2. And what this relationship does is it saves us a tremendous amount of time so that we don't have to use the Pythagorean theorem to solve for the lengths of one of our sides. So in this example, I've got one side that is 10 root 2 units, one side that's marked x, and we're going to find the length of x in this 45-45-90 triangle. So first of all, let's identify the parts. I know that x is a leg, because it is opposite a 45-degree angle. This other side that's not marked would also be considered a leg because it has to also be x units in length. Then the side labeled 10 root 2 units long is the hypotenuse because it is opposite the right angle. The side opposite the right angle is always your hypotenuse. So if I take that relationship that we talked about earlier, where we know the hypotenuse is always going to be equal to the length of a leg times root 2, and I start plugging in the parts into that relationship, I generate an equation that I can then solve to find the length of the side labeled x. And so to solve, I'm just going to divide both sides by root 2, and we'll find out then that x has to be 10 units. So the next thing is I would like for you in your notes to practice an example of a 45-45-90 triangle. And what I want you to do is to find the missing lengths in each triangle and give your answer to 2 decimal points. You can use your calculator to find the actual answer and round it to 2 decimal points, but you should use the key relationship discussed earlier about 45, 45, 90 triangles to set up an equation to solve for both x and y. At this time, you should pause the video and work on question number 138 in your notes. So the solution for this particular triangle for x is about 2.12 units. So x is a leg, 3 is the hypotenuse. We plug those values into that key relationship we talked about with 45, 45, 90 triangles. We come up with the equation 3 is equal to x times root 2. And so to solve for x, we're going to divide both sides by root 2. And again, we're going to plug in 3 divided by the square root of 2 into the calculator and round that answer to 2 decimal points. And that's where we come up with 2.12. Since x and y are both opposite angles that are congruent, x and y have to be congruent in length. So x and y are essentially both legs of this 45, 45, 90 triangle, and therefore y also has to be 2.12 units in length. A second special triangle that we want to talk about are 30, 60, 90 triangles. And you may remember these from geometry, but let's take a step back and talk about where the 30, 60, 90 triangles come from. If we start with an equilateral triangle, equilateral meaning all three sides are the same length. We've chosen a random side length of 2 units as an example. We can draw the altitude from any one vertex. We'll go from the top all the way down to the bottom, and that creates 2 separate right triangles that are congruent. It'll split this top 60-degree angle into 2 30-degree angles. And notice that by drawing that altitude to the opposite side, I also split that other side length, which was 2 units long, into 2 congruent parts, both 1 unit long. So essentially I can take those 2 congruent triangles and split them into equal parts, and what I would have then is a 30, 60, 90 triangle. So all 30, 60, 90 triangles then are half of an equilateral triangle. And because we know that 30, 60, 90 triangles have to be half of an equilateral triangle, one key relationship that we know for sure is that the length of the hypotenuse, which in our example we labeled 2 units long, is always going to be twice the size of the shorter leg, right? And I know that this side, which was half of our equilateral triangle, is the shorter leg because it's opposite the 30-degree angle. Right? This opposite side of the 60-degree angle would be the longer leg, and the side that's labeled 2 units is the hypotenuse because it's opposite the right angle. And one key relationship to keep in mind, again, is with all 30, 60, 90 triangles, the hypotenuse is equal to the shorter leg times 2. So if we wanted to find the length of the longer leg, we could use the Pythagorean theorem. But again, that's going to become tedious, and the purpose of these key relationships is a more efficient way of expressing the relationship between the lengths of the sides. But for the sake of explaining where this second key relationship comes from, if we take a look at the Pythagorean theorem with the side lengths given here, we would find then that the length of the longer side has to be the square root of 3 units, right? Or 1 times the square root of 3. And therefore we come up with the second key relationship is that for any 30, 60, 90 triangle, the length of the longer leg will always equal the length of the shorter leg times the square root of 3. So all 30, 60, 90 triangles have 2 key relationships that you want to keep in mind. Again, the hypotenuse is the shorter leg times 2, and the length of the longer leg is equal to the length of the shorter leg times root 3. So if we take those 2 key relationships, we can use them in an example to solve for either of the legs or the hypotenuse length. Now, what's important for you to understand here is, with this example, because I only know the length of one side, without knowing these key relationships, I have no other way of finding the lengths of the other 2 sides. There's too many unknowns. But if I know these key relationships, I can use them to set up equations that I can then solve that will allow me to find the lengths of the two missing sides. So for this example, let's start with identifying what each labeled side represents. The side labeled 10 units is the shorter leg because it's opposite the 30-degree angle. The side labeled A is the longer leg because it's opposite the 60-degree angle. And the side labeled B is the hypotenuse because it is opposite the 90-degree angle. So when I insert those values into the two relationships, I come up with two different equations that I can then solve to find the lengths of each of the unknown sides. Like what I come up with is that B is 20 units, or the hypotenuse is twice the length of the shorter leg. And I also come up with then that A is 10 times the square root of 3 units, or the longer leg is equal to the shorter leg times the square root of 3. So what I'd like for you to do next then is to again pause the video, take some time, and in your notes complete question number 140 as an example, in which you're going to find the lengths of the two missing sides, x and h, and use your calculator to give your answer to 2 decimal points. So for this example, first of all, if we start by identifying the parts, x is the shorter leg, since it's opposite the 30-degree angle, or the smallest angle. 7 is the length of the longer leg, since it's opposite the 60-degree angle. And h represents the hypotenuse, since it's opposite the right angle. And so if I plug in these values into those two key relationships we talked about, what I end up with is two equations. And what you should notice is the second one cannot be solved because there's too many variables. The length of the shorter leg must be known in order to find the hypotenuse. And so I have to solve the other relationship first so that I'll know the length of the shorter leg. And so if I take this equation, I can solve by dividing both sides by the square root of 3. And I'll end up with then that x, or the shorter leg, is approximately 4.04 units in length. And once I've got that length, I can take it and plug it into the other equation for the length that we marked x, or my shorter leg, and solve for the length of the hypotenuse, which is going to be twice the length of the shorter leg, or 8.08 units. The final objective for the day is adding and subtracting radicals, and this is again a review topic, so we won't spend a lot of time talking about it, but I will review a couple of key things here. First of all, you have to have the same radicand in order to add or subtract two radicals. So the square root of 50 minus the square root of 8 does not equal the square root of 42. We have to simplify these radicals, and the only way we'd be able to add or subtract them is if the radicands happen to be the same. Think about adding or subtracting like terms, basically. So if we simplify the square root of 50 to be the square root of 25 times 2, or 5 root 2, and we simplify the square root of 8 to be the square root of 4 times the square root of 2, or 2 root 2, because the radicand, root 2 and root 2, are the same for both, I can subtract these radicals by simply subtracting their coefficients. Essentially what I have is 5 square roots of 2, and I'm going to take 2 square roots of 2 away, and I will have 3 square roots of 2 left. Much like if I had 5x minus 2x, that solution would be 3x. So again, adding and subtracting radicals is much like adding and subtracting like terms. You have to have the same radicands in order to add or subtract any radicals. So finally, I would like for you to try one example of adding and subtracting with radicals. Again, this is from your textbook number 80. So at this time, you should pause the video and complete question number 80 in your notes. And when we simplify these radicals, the square root of 18 simplifies to be 3 times the square root of 2, or the square root of 9 times the square root of 2. This 2 times the square root of 50 simplifies to be 10 root 2, or 2 times the square root of 25 times the square root of 2, which is 2 times 5 times root 2, or 10 root 2. So once I've got both radicals simplified, I recognize that they have the same radicand, and so I can add them then by combining their coefficients. 3 roots of 2 plus 10 roots of 2 is equal to a total of 13 square roots of 2, and that would be our final answer. So this concludes our notes on section 7.4. You should be able to use the self-checks that you completed for homework last night, along with the notes and examples from today, to then complete homework 24. And you can use the duration of the class period as well as the necessary amount of additional time tonight then to complete this assignment for tomorrow's class. Have a great day.